Welcome back, everyone. Um, Today we're diving into something pretty fascinating, the impact of both supervised fine-tuning and reinforcement learning on how well foundation models can generalize, go beyond the data they've been trained on.
Right. Yeah, it's a big question in the field right now.
Yeah. And, you sent over some research on this. SFT memorizes, RL generalizes, really interesting stuff.
Hmm.
And it really digs into this comparison between these two techniques.
It does, yeah.
So I guess maybe we could start with what are the big areas of generalization that we're going to be looking at here?
Sure. So the paper focuses on two main types, textual rule-based generalization and visual generalization.
Okay, so textual rule-based generalization,
Yeah.
that's basically like a model applying rules. It's learned to kind of new situations, new variations of things.
Exactly. So it's about, can the model take what it's learned and apply it to things that are similar but not exactly the same as what it's seen before?
Got it. And then visual generalization, that's all about handling changes in the visual input, right? Even if the task is the same.
Right, exactly. So for example, if a model is trained to recognize cats in images, can it still recognize cats if the lighting is different or the cat is in a different pose?
Okay, makes sense.
Mhm.
Now, the research used a couple of different environments to test these types of generalization, right?
Yeah. They used something called GeneralPoints, which is it's a card game kind of like that classic 24 game.
Uh,
And then they also used V-IRL, which is a real-world navigation task.
oh, interesting. Okay, so general points, we've got cards involved. I'm intrigued. Tell me more about that one.
Sure. So in GeneralPoints, you get 4 cards, and these can be presented as either just text descriptions or actual images of the cards.
Yeah.
And the goal is to come up with an equation using basic arithmetic that equals 24, using each card's value just once.
Okay, kind of like a puzzle.
Exactly. And they use this game to test textual generalization by changing up the rules. Like, for example, sometimes the Jack, Queen, and King cards represent their traditional values, but other times they might all be assigned the value of 10.
So the model has to adapt to different ways the game can be played.
Right. And then on top of that, they also test visual generalization by changing the appearance of the cards. So, for example, they might train the model on cards with black suits and then test it on cards with red suits.
Oh, wow. So even if the model knows the rules, it still has to figure out what it's actually looking at.
Exactly.
Okay, and what about that other environment, V-IRL?
So V-IRL is all about navigation in the real world. The model is given instructions, which include spatial information, and it has to figure out how to get to a target location.
Okay, so landmark recognition is going to be key there, right?
It is absolutely. So to test rule generalization in this environment, they used 2 different ways of giving directions. One was using absolute orientation, like northeast, southwest, and the other was using relative orientation, like left, right, slightly left, and so on.
Hmm. I see. So the model has to adapt to different ways of understanding directions.
Exactly. And then for visual generalization, they did something pretty interesting. They trained the model on routes in New York City
New York.
and then tested it on routes from all sorts of different cities around the world. So the model has to deal with completely new visual environments.
Wow, that's a tough challenge.
It is. It's a really good test of how well the model can transfer its knowledge to new situations.
So they applied both supervised fine-tuning and reinforcement learning in these environments using, I think you said the Llama 3.2 Vision 11B model.
That's right. Yeah. They wanted to see which approach would lead to better generalization.
And I'm guessing the results are what make this deep dive so interesting, right?
Wait.
Which one's better?
They are. And you might be surprised by what they found.
Okay, well, now you've got me hooked. Let's get into those findings then.
Sounds good.
All right, so let's talk about what they discovered. So spill the beans. What did the researchers find out about which method was better at generalization?
Well, they found that reinforcement learning consistently did better than supervised fine-tuning when it came to generalizing, both in the textual domain and the visual domain.
Oh, wow. RL really pulled ahead. Huh. So it was able to adapt to new rules and those visual variations they threw at it.
Yeah. I mean, like in GeneralPoints, for example, reinforcement learning led to significantly better performance.
Hmm.
Especially when those rule variations were in play, like assigning different values to the face cards.
Right, right. So SFT had some trouble with that, I guess.
It did, yeah. It kind of showed this tendency to just memorize the training data, which, didn't really help it when it was faced with something new.
That makes sense. So it couldn't really go beyond what it had seen before.
Not as well as RL could, no.
Okay, so RL was better with the rule variations.
Yeah.
What about those visual variations, like with the different colored cards?
RL actually excelled there, too. It was able to recognize the cards and solve the equations even when the colors were different from what it had seen during training.
Hmm. Interesting. So it was really able to generalize those visual features.
It was. It was pretty impressive.
What about in that V-IRL environment? How did things shake out there?
Well, in V-IRL, reinforcement learning achieved state-of-the-art performance, which is pretty huge.
Wow, state of the art. Okay, so it was able to like really nail those navigation tasks.
It did. It actually outperformed previous results on the V-IRL mini benchmark by a pretty substantial margin, like 33.8%.
Oh, wow. That's a big jump.
It is, yeah. And it showed a really strong ability to generalize both the rules of navigation and those visual features of the different environments.
Hmm. So it could handle new cities,
Yeah.
new landmarks, the whole nine yards.
Exactly. It was able to adapt and figure things out in those unseen locations.
SFT didn't fare so well, though, I take it.
No, it had a much harder time with those tasks.
Okay, makes sense.
Yeah.
So RL is clearly the winner when it comes to generalization.
Mm.
But the study also looked at something else, right? Something about RL's impact on visual abilities.
It did, yeah. And this was one of the really interesting things they found. It seems like RL, especially when it's trained with like an outcome-based reward function, actually improves the model's underlying visual recognition abilities.
Oh, wow. So it's not just about making better decisions. It's actually like changing the way the model sees things.
That's what it learned both. And I think this might be why RL did so well in that GPVL environment, with the cards.
Because it could actually see the cards better, even with the color variations.
Right. It was able to pick up on those subtle differences that SFT missed.
Hmm. That's fascinating. So RL could be a valuable tool for improving not just decision-making, but also like visual capabilities in these vision language models.
It could be. It definitely opens up some exciting possibilities.
It does. Now, even though RL seems to have the edge here, SFT still played an important role in the training process, right?
It did, especially because the base model they used, Llama 3.2, had it had pretty poor instruction following abilities.
So they needed something to kind of get it up to speed.
They did, and that's where SFT came in. It acted as this sort of format teacher.
A format teacher.
Yeah, basically it helped the model learn how to structure its responses in a way that made it possible to do effective reinforcement learning.
Oh, I see. So without that initial formatting, help from SFTRL wouldn't have been as successful.
Exactly. In fact, when they tried doing end-to-end RL without SFT, it just didn't work.
Didn't work at all.
Not really. The model produced these really long, rambling responses that were just useless for extracting rewards.
Okay. So SFT kind of laid the groundwork for RL to come in and do its thing.
Yeah, you could say that.
Okay. Now, there was one more thing I wanted to touch on, those verification iterations.
Yeah, right.
So remind me, what are those again?
So verification iterations are basically like giving the model multiple chances to revise its answers based on feedback from a verifier.
So it's like having a teacher check your work and tell you where you went wrong.
Yeah, it's kind of like that. And what they found was that scaling up the number of verification steps during RL training led to even better generalization.
Really? So the more chances the model had to kind of think things through and correct its mistakes, the better it got at generalizing.
Exactly. And this was especially true for out-of-distribution performance, when the model was faced with stuff it had never seen before.
So just one verification step didn't do much.
It made a little bit of a difference, but when they increased the number of steps, like to 3, 5, or even 10, they saw significantly greater gains in ode performance.
That's pretty amazing. So giving the model that extra time to learn from its mistakes really paid off.
It did. It really highlights how important that iterative feedback process is for helping the model develop that deeper understanding and that flexibility it needs to generalize well.
I see. It's like the more it practices and gets things wrong and corrects itself, the more adaptable it becomes.
Exactly. It's like learning from experience.
It makes sense. So all in all, it sounds like this research makes a pretty strong case for RL as a powerful tool for generalization in these complex tasks.
It does. It really shows how RL can help models go beyond just memorizing patterns and actually learn how to think for themselves.
It's like teaching them to learn rather than just teaching them to know.
Yeah.
Wow. So it really seems like from all this, that reinforcement learning has some pretty significant advantages when it comes to generalization, both when we're talking about text and visual stuff.
Yeah, I'd say that's a fair takeaway. I mean, the fact that it can actually enhance those visual capabilities, that's a pretty big deal,
It is.
Yeah.
It's pretty amazing to think about, that we can use these techniques not just to help models make better decisions, but also to actually change the way they see the world.
It is, yeah. I mean, just imagine the possibilities for improving these vision language models, not just for like specific tasks, but for a whole range of applications.
Exactly. It's really exciting stuff. Well, I want to thank you so much for taking this deep dive with me. It's been a really illuminating conversation.
Oh, it's been my pleasure. I always enjoy getting to chat about this kind of research.
And to everyone listening out there, thanks for joining us on this deep dive. We hope you found it insightful and maybe even a little bit mind-blowing. And keep those curious minds engaged, because there's always more to explore and discover in the world of AI. So until next time, stay curious, everyone.